Okay. Hello. How can imaging sensors support industrial machine vision applications, especially ST sensors, of course? My name is Bollinger. I'm in charge for technical marketing activities and imaging sensors at ST, in charge for the German-speaking area. And I will tell you in a few minutes how this target can be achieved with ST camera sensors. So we are today in an eternal pixel race, faster, smaller, cheaper. Is this really true? Yes, it is true, because ST can provide faster sensors, smaller sensors, and because they are smaller, of course, they are also cheaper. How can this be achieved? ST was in the past the Nokia camera. This was a long time ago. In between, we have done automotive camera sensors, but automotive is very expensive due to the automotive grade. And we have done the last year an activity where we completely removed from these camera sensors, automotive grade, the full automotive grade, the safety, the security, and immediately the sensor became small, cheaper, and better. Why better? Because we are using automotive pixels. They have two features. Number one is that the pixels are isolated, trench isolated. This means the photon arrives where it should arrive, at the pixel and not at the neighbor pixel. This is improving the quality. And the second point is we have backside illumination. This means the photons, the light, comes from the backside to the chip and not passing through the materialization of the chip itself. Means also less crosstalks and better performance. So these two features, backside illumination and diode isolation from the automotive, allow us to have very small pixels with high quality. And this is what we're using. So the more the better. Is this true? The more pixels, the better? No, not really. We don't speak about mobile phone market. We speak about industrial market. And industrial market do not need the 10, 20, 50 megapixel. We are pleased with a few hundred kilopixel, 105 megapixel, 5 megapixel. This is enough for industrial application. So again, as I said, backside illumination and trench isolation are supporting the quality of the sensor, even with a small pixel. And the other thing is, we have two chips. We are using two chips, which we bond together. One chip is the imaging sensor with the pixels, optimized for pixel design. And the other one is an analog digital circuitry where we integrated ISP functionality. Means the sensor is supported by functionalities like cropping, like binning, and much more features which I explained to you, which are decreasing the demand on a microcontroller, on a microprocessor. At the end, we don't need any MPU anymore. We don't need any ISP. We simply have the sensor, an MCU by ST, STM32, and this is enough to visualize and to stream pictures. So, two devices bonded together. You from externally just see one device, which is in the camera module. Good. So, I just give you a flavor about the features which we have implemented. For example, auto wake up. The sensor is supervising the picture which he has. If there is a change in the picture, he starts to stream. Or the MCU can give the command, please start streaming, and then we need a little bit more of power. And when the target who was moving in the picture is disappeared, we go back in the idle mode. So we call this auto wake up. This is decreasing the power consumption. This is decreasing the data width, the data speed which we have, and we just transfer important information. Typical example is the animal camera in the wood outside, which should only activate when the fox comes. If there's no fox, no picture, low power. Low power in our sense means milliwatt in the standby condition and a few 10 watt in streaming condition. When I started with imaging pictures 15 years ago, the cameras took 1 watt. Now we are in milliwatt area. So this auto wake up is important to have a low power application, battery driven application, and the circuitry which is integrated supports with GPIO a command to MCU, please stream, and then we go. Another industrial application or example is the the conveyor belt. So as long as there's no packet on the conveyor belt, we don't stream. We just supervise the belt. If there's a change, as long as there's no change, we don't stream. We are in low power. Once the packet is arriving, we go with a command to the MCU, please stream, and then we go. Once the packet is disappeared, we go back again in this auto low power mode, save power, save bandwidth, and only transmit data if there's something to tell, like in the real world. Another feature is background subtraction mode or differential mode. What we can do is we can compare two consecutive pictures, 2 frames, and see if there's a change. If there's a change, it is our target which we want to see, and in the same time, sorry for the nervous laser, this is not mine, at the same time we can also remove the background. This is a typical feature which we know from the video conferencing. Background is not requested, not important. Simply to compare 2 following frames, we can see what is important, what is moving, and the rest is eliminated. So background removal is one of these digital features which we are able to provide, again, reducing data bandwidth, data rate, frame rate. Now, we do a transition. In the past, we were taking photos, everybody knows, with a mobile phone, taking a photo, looking to the photo. This is not true anymore for the industrial application, because we go now from imaging to sensing. We want to extract information in order to control something. This means really a transition from imaging to sensing. Means in the past we took the picture, we looked to the picture, we enjoyed the picture. Then we started to use the picture, cameras in the public traffic, transportation, these kind of things. And now, today and tomorrow, we are using AI information, AI concepts, in order to extract information and to use them. Yeah? So this is a transition which we're actually following, which we can support with our sensors, and which we also can support with our MCUs, who have today AI access, have neural networks inside. So AI is the key application in future for the cameras. Eye tracking. This is just an example of tracking objects. This is not the eye, it's a fork. But we can track objects in the scene, in the photo, and activate the sensor, transport only the delta, something is moving. And again, this is something which is extremely usable in the industrial world. We can see cars moving, we can see packets moving, we can see hands, so gesture control, people counting, all these things are possible once we are able to trace in the picture or with the picture some movement. We can use it, we can do calculations, and then we are at sensing level. Not anymore on picture level, but really on sensing level. And this can be used to have new applications in the industrial world. This is another feature of our 1.5 megapixel sensor we call optical flow. We have 1.5 megapixel, and we can extract 2,000 motion vectors. Means we take one pin, we take around the pixels of this 1 pixel, and this is creating a motion vector. In the scene, we have 2,000 vectors. We can extract them, and we can use them to see if things are moving, like this car, like my colleagues waving, like my colleagues turning pages on a side. So if the picture itself is not requested because of privacy reasons, we still have the motion vector. You don't recognize anybody with these few pixels, but you have the motion. Motion vectoring is here the key argument, which is implemented in our 1.5 megapixel sensor. You simply have to extract it and to use it. Very simple. Again, the picture itself is something which in Europe is sometimes not really requested, preferred. But here we have the picture, the main information in the motion vector. If the picture is requested, we use it. If not, we just use these 2,000 vectors and we have the motion in the picture. So now we go from the sensor, because ST does not only have sensors, to the system itself. What we can propose today, and we have demos on our booth showing this, we can use one of our sensors. We have MIPI interface as a standard camera interface, or if the MCU or the controller doesn't have MIPI, we have alternatively ICCC. By this, we connect our sensor to the MCU using a STM32H5 or H7. Does also have the AI segmentation. And by this, we have a simple, cost-effective solution, imaging on one side, AI on the other side. We have a demo on the booth where we show that we follow the fingers of a hand and we see the segments of the finger and we translate this in a waving device externally. Yeah. Using AI, using a simple sensor, extracting the main information, the position of the finger, and then translating this in something different. So we have the imaging capture, we have the downsizing, cropping, zooming, whatever is needed, implemented in the sensor, ICCC, the counter interface, and then the other software who can treat the data which we are extracting. So how can we support you as a customer to use it? ST is a chip maker. So we deliver primarily only the die, reconstructed wafer, and the customer should take care with our help how the sensor can be implemented into a camera. We have partners doing this, so these partners can provide the module with an optic, with a flex cable. This is one of the critical items, how to connect the camera to the system. And these camera modules are coming from our partners in Israel, in China, but also Jabil in Jena. They are able to translate our chips into a module. Jena or Jabil does it customized. The Chinese partners have fixed modules, so you have to take them as they are. So these are the modules. Again, ST is delivering today only the bare die, but our partners can put these dies into modules, and you can buy the modules directly from these partners or from distributors. Our standard distributors have these modules listed and they are available. How do we continue? So we have the camera modules. We have an evaluation kit. We have it on the booth to show you. The camera is connected to the evaluation kit. We can connect either by USB, a PC with a GUI, or a STM32 evaluation board, or a Raspberry Pi. And by this, you can start to build up a camera system and to use our PC evaluation software, Linux drivers, script generators. And once you are proceeding, we have an extremely documented website on st.com giving to you the data sheets, the user manuals, all those things which are necessary to write software, to implement software, and to use the board and the sensor itself. We have getting started, we have tutorials, we have web meetings to bring it closer to you. And of course, we have also reference designs. In case, as I said, you are not able to do a camera on your own, we have module maker partners in China, in Israel, and here in Jena. We have software providers who can help you to implement more software as we provide it. And of course, we have also integration service partners who can do a full integration for you. Okay, now it's time to wrap up, just to summarize a little bit. The pursuit to race towards smaller pixels with improved electro-optical performance is what we translate from automotive to consumer industrial devices. Super sensors, small, effective, low resolution, low price. This is very important. Evolution of the vision market towards computer vision and edge AI applications is questioning the concept of imaging data. So again, the step from image, looking to image, to information which we can extract and reuse for AI applications. New seek for optimized swap, size, weight, power, cost, calls for integrated architecture, embedded smart features and turnkey developments. These are the digital functions which we put in the second chip on top over the optical pixel design. And by this, we're offering a full solution which does not need an ISP. ISP functionality is inside. which needs just a simple microcontroller, STM32. That's it. All tools are based on this concept. Integrated stacked architecture, embedding relevant data optimization features will become a must-have. Means the market is now moving to this kind of AI application, sensoring. The keyword is sensoring. How can we extract from the camera sensor informations which can be reused to control something, to supervise something? So sensing is now the key feature of a camera. It's not anymore the picture. We leave the picture for the mobile customers, high resolution, but this is not the market. We are looking for the industrial solution where a simple camera sensor can provide the necessary information for AI applications. So, if you want to find out more about these camera sensors, as I said, we have 3 today, 400, 600, 1.5 megapixel. The 5 megapixel will come soon, end of the year. Go to st.com, search for BrightSense imaging sensors. You find there everything. We can show you some demos on our booth just around the corner. I will show it to you. For example, this finger demo with a camera. Or you can contact me personally after the show for some detailed discussion, a Teams meeting, but also to demo something and discuss your application. If there are any questions, come to me now, or you can also visit us on the booth. I go back. On the booth 320, which is just around the corner, where we demo the camera applications. As I said, the finger application is there, but also time-of-flight sensors. If the picture, the face, is not requested, not wished, we can do nearly the same functionality with a time-of-flight sensor, 8 by 8 pixels, and do the same kind of applications. Mean we can see moving things, we can see a hand, we can see products, we can count products. So one-time picture, camera, no picture, time-of-flight sensors. Thank you. Questions? Thank you.